Hello guys, my name is IBM and today I want to teach or I want to take you through thermodynamics. We are dealing with the thermal properties which has three areas. We saw ideal gases and today I want us to see thermodynamics which is also under thermal properties. So without wasting time, I just want to remind you that this is the Cambridge curriculum. This is the Cambridge curriculum and this is physics 9702, that is A-level physics, and this is actually going to be paper 4. Just to remind you of the topics that you are supposed to cover in A-level physics paper 4. These topics include circular motion, which I already recorded, gravitational fields, which I will record later on, ideal gases, which I've already recorded, uh, temperature, which I will record later on, thermodynamics, which I will be recording today. Remember ideal gases, temperature, and thermodynamics, I call them thermal properties. So I consider them as being one topic. That's why you see it is 3.1, 3.1, 3.3. Simple harmonic motion, that one I've already recorded it. Oscillations, I've already recorded it. Electric fields, I'll record that later on. Magnetic fields and electromagnetic induction, I will record that later on. Capacitance is already recorded. Alternating current is already recorded. Nuclear physics is already recorded. Quantum physics, I'll record that later on. Astrophysics and cosmology is already recorded. Medical physics, I'll record that later on. And currently, I'm going to be recording thermodynamics. So let's go to thermodynamics, which is under thermal properties. So do not forget the general topic can be called thermal properties, which, like I said, it includes ideal gases, which we have already recorded. It includes temperature, which I will record later on, and it also includes thermodynamics, which I'm going to record. So let's go to thermodynamics. So in thermodynamics or under thermodynamics, we are going to cover two major important areas, and that's what makes this one very short. It's going to be just one lesson. Thermodynamics, we shall cover internal energy and the first law of thermodynamics. And when internal energy is covered, and the first law of thermodynamics, then the chapter, the concepts of thermodynamics, the concept of the topic thermodynamics will be actually done. So let's start by introducing the term internal energy. What do we mean by internal energy? So what do we mean by internal energy? Of course, from your IGCSE physics, you remember the three states of matter. And from ideal gases, we talked about the kinetic theory of matter, where we saw that matter is made up of small particles, which are called molecules, or you can call them atoms. And matter was existing in the three states, that is the liquids, solids, and gases. So the liquids, solids, and gases could be characterized by looking at the difference in the arrangement of their molecules and their motion. Therefore, the molecules are arranged differently in solids, liquids, and gases, and the molecules also have some motion. So this arrangement of molecules and the motion of molecules could be responsible for the internal energy of a substance, or for the internal energy of matter. So liquids, solids, and gases could be characterized by differences in the arrangement, order, and motion of their molecules. We could equally have said that in the three phases or in the three states of matter, the molecules have different amounts of kinetic and potential energies. Remember, the molecules are arranged differently in the three states, and the molecules move actually differently in the three states, as we saw under ideal gases in the concept called the kinetic theory of matter. Remember, we saw that the liquids have their molecules moving randomly, freely, and sliding past each other. That means the molecules had kinetic energy. But there was some weak force of attraction between the molecules, and therefore the molecules have some potential energy. The potential energy is due to the force between these molecules and their separation. Then in solids, we saw that the motion of the particles is restricted to vibration about their equilibrium position, because solids have a property which we call rigidity. So the molecules vibrate about the same position. And then for gases, the molecules are free to move randomly in all directions, occupying the whole container in which the gas is placed. So the molecules have kinetic energy. However, the molecules, even though they are far from each other, they experience some little force and therefore they still have some potential energy between them. So we could equally have said that in the three phases or in the three states of matter, the molecules have different amounts of kinetic and potential energies. Thus, we find the internal energy of an amount of matter by simply adding up the kinetic and the potential energies associated with all the molecules that make up matter. So we look at the kinetic energy part and the potential energy part of all the molecules that make up the matter to find what we call the internal energy of that matter or the internal energy of the substance. Therefore, we can define internal energy of a system as the sum of the random distribution of the kinetic and the potential energies of all the molecules that make up the system. The sum of the random distribution. It is the sum of the random distribution of the kinetic and the potential energies of all the atoms, or called the molecules, which make up the system. Why am I referring to the random? Because from the kinetic theory of matter, the molecules are in continuous random motion as verified by Brownian motion for liquids and solids. Then the molecules have their energies distributed randomly. Therefore, internal energy of a system is the sum of the random distribution of the kinetic and the potential energies of all the atoms or molecules which make up the system. So internal energy is going to be the kinetic energy plus the potential energy of all the molecules which are making up the system. Let's try to extend the idea of internal energy further. Let's talk about a liquid. What do we know about a liquid? Of course, in a liquid, we know that the intermolecular forces, that is the forces between the molecules, are very strong, or they are stronger as the molecules are closer together. That is in comparison to the gases. So it means the potential energy contribution to internal energy becomes more significant here because the force between the molecules are relatively stronger. The kinetic energy contribution is due to the random motion of the molecules. Because the molecules are free to move, they have kinetic energy. Because the molecules are slightly far from each other in liquids and experience some force, they have potential energy. So when we talk about the internal energy of a liquid, the internal energy of the liquid will be the sum of the kinetic energy of the molecules and the potential energy of the molecules that make up the liquid. If we talk about a solid, in a solid is also made up of atoms or molecules, but these atoms vibrate about their equilibrium position. They oscillate about the same position, which means these molecules have kinetic energy due to these vibrations. And the potential energy contribution is going to be caused by the strong binding force between the atoms. And the kinetic energy contribution is due to the motion of the vibrating atoms. So the force due to the binding force between the molecules is responsible for the potential energy because to break these bonds between the molecules would require a lot of energy. And then the kinetic energy component is going to be contributed by the vibration of the atoms. Therefore, the internal energy of a solid is also equal to the sum of the random distribution of the kinetic and the potential energy of the molecules that make up the solid. Let's think about a real gas or a normal gas. For a real gas, the molecules of a real gas exert force on each other. Therefore, these molecules also experience or they have potential energy due to the force between the molecules. So at any instant, there will be certain potential energy associated with the positions that the molecules occupy in space because they exert a force on each other, even though the force is extremely weak. Because the molecules move randomly, these molecules which make up the gas move randomly, the potential energy of a given molecule also vary randomly. The molecules of a real gas also collide with each other and interchange kinetic energies during the collision. So these molecules which make up a real gas have both potential energy due to the weak force between the molecules, and because the molecules move randomly, the potential energy uh, of a given molecule also vary randomly. The molecules have kinetic energy because they are moving freely. And during collisions, they can interchange their kinetic energies. So the kinetic energies they have is also randomly distributed. So for real gas, therefore, the internal energy can also be equal to the sum of the kinetic and the potential energy of the molecules that make up the real gas. So one important thing we need to note about the real gas is that it has there is some weak force of attraction between its molecules, and because there is some weak force of attraction between its molecules, then the potential energy component cannot be ignored, and therefore the internal energy of the gas would be the sum of the potential and the kinetic energies of all the molecules of the gas. Do not forget that the energies are distributed randomly. So the sum of the random distribution of the potential and the kinetic energies of all the molecules that make up the gas would be the internal energy for real gas. One important thing we need to note is if the gas is ideal. We talked about ideal gases in the previous chapter, where we said for an ideal gas, the molecules are infinitely far from each other. The molecules are infinitely far from each other so that the force of attraction between the molecules is negligible or can be neglected. And because the molecules are infinitely far and the force between the molecules is negligible, so it means the intermolecular forces can be considered negligible. And because the intermolecular forces determine the potential energy, so it means the potential energy associated with molecules in an ideal gas is negligible and approximately zero. So for an ideal gas, the potential energy component is zero. And remember, internal energy is the sum of the random distribution of the kinetic plus the potential energy of the molecules. And since the potential energy part is zero, then it means for an ideal gas, internal energy is simply going to be equal to the sum of the random distribution of the kinetic energy of all the molecules which make up the ideal gas. So for an ideal gas, we don't talk about potential energy because the intermolecular forces are considered negligible and equal to zero. So the potential energy associated with the molecules is approximately zero. Thus, for an ideal gas, the sum of all the kinetic energies of all the molecules due to their random motion is what we call the internal energy of the ideal gas. So you should define internal energy for the ideal of an ideal gas as the sum of the random distribution of the kinetic energies of all the molecules that make up the ideal gas. Not forgetting that the potential energy component does not contribute to the internal energy of the gas because the molecules are infinitely far so that the force between them is assumed to be negligible. So that is the internal energy of an ideal gas. A few things we need to note about this concept. I want you to note that potential energy of a material depends on the separation and the force between molecules. And the greater the separation, the greater the potential energy. But remember, it is maximum and is zero at infinity. The greater the separation between the molecules, the greater the potential energy. But remember, at infinity, it is maximum and it is zero. We shall talk about the same concept under electric fields and under gravitational potential and under a concept called gravitation. Potential energy depends on the separation between the molecules and the force between the molecules. If the force between the molecules is negligible, it means the molecules are infinitely far from each other, so the potential energy is zero. And of course, it is maximum at infinity, but it is zero at infinity. However, one important thing I want to remind you is that during melting and boiling, kinetic energy does not change. The kinetic energy of the molecules does not change. That's why when a liquid starts boiling or when a solid starts melting, even if you keep the thermometer in the liquid or in the melting solid, the temperature or the reading of the thermometer remains constant because during change of state, the energy which is supplied does not go into changing the kinetic energy of the molecules. but the energy goes into breaking the bonds, increasing the potential energy. Because as the bonds are broken, the molecules move further apart, the potential energy increases. So during melting, the kinetic energy of the system or the kinetic energy of the molecules does not change. That's why the temperature remains constant, but the potential energy increases as the energy supplied goes into breaking the bond. So the energy supplied or the thermal energy supplied is used to increase the separation between the molecules. That is breaking the bonds, breaking up the bonds between the molecules. And of course, as the molecules move further apart, the potential energy increases. The potential energy increases because remember it is maximum at infinity where it is actually zero. Okay, I will talk about this other concept under a unit called under the next part, which is called temperature, where we shall discuss our thermal properties in more details. So how do we therefore increase internal energy and how do we decrease internal energy? So the internal energy of a system can easily be decreased or can easily be increased by simply um, for example, if we heat the system or we heat if the system is a gas, we can increase the internal energy of the gas by heating. If the gas is heated, it means heat is added to the system. Therefore, that heat should do something onto the system, which is most likely going to increase the kinetic energy of the molecules. And if the kinetic energy of the molecules are increased, or if the molecules even move further apart, it means the potential energy part could be increased. In both cases, heating of the gas increases the internal energy. It increases uh, the, the kinetic or the potential energy of the gas, therefore internal energy increases. Number two, we can increase the internal energy by doing work on the gas, especially by compressing. Imagine if a gas is compressed. Imagine if a gas is compressed into a small volume. That is, the volume decreases. If the volume decreases, if the volume decreases, remember from the ideal gas equation, we saw that PV is equal to nRT. And if the volume decreases, it means the pressure is most likely going to increase. If the pressure remains constant, then it means if the volume decreases, so since we can't have pressures constant, so if the volume decreases, the pressure increases. And if the pressure increases, then the temperature could be increased because the temperature is directly proportional to the pressure. So if a gas is compressed, we expect that the molecules move faster and collide with the walls of the container more rapidly. They can bounce off more oftenly and they can bounce off more rapidly from a moving wall if the wall is moving inwards. So they gain more kinetic energy. And if they gain more kinetic energy, it means the kinetic energy part of the molecules has increased, and therefore the internal energy is expected to increase. Therefore, doing work and heating both involve transfer of energy into a given system. By this time, the transfer is by different means. For example, heating could be different from doing work because work is actually mechanical, because you are trying to compress a system that is mechanical. Yet heating could be just applying energy or adding energy to the system indirectly. So both involve transfer of energy but by different means. We can also decrease the internal energy of a system. We can decrease internal energy of a system. And how do we decrease the internal energy of a gas, for example? The internal energy of the gas can be decreased by doing the opposite to what we did in the previous part. For example, a system could be left to lose heat to its surrounding, or a system could be allowed to expand so that it does work onto its surrounding. In both cases, if a system loses heat, the kinetic energy of the molecules may decrease. And if the kinetic energy of the molecules decreases, then if the kinetic energy of the molecules decreases, remember internal energy is the sum of the kinetic energy of the molecules plus the potential energy. Let's say the gas is ideal and the potential energy is zero. So if the kinetic energy of the molecules decreases, then the internal energy also decreases. If a gas expands, for example, doing work to the surrounding, the volume is increasing. The work done is using up the energy which is already within the system. Therefore, still it means the system is losing energy to the surrounding by doing work, and therefore internal energy also decreases. So this therefore leads us to what we call the first law of thermodynamics. The first law of thermodynamics. Remember in your AS physics and IGCSE, you talked about the principle of conservation of energy, where you mentioned that can neither be created, energy can neither be created nor destroyed, but energy could carefully be transferred from one form to another. Similarly, if you apply heat to the system by say heating, or if you add heat to the system, that heat should not disappear to anywhere. That heat can do things, it can cause work to be done, or it can cause a change in internal energy. So by conservation of energy, any change in internal energy could be as a result of applying heat to the system, or as a result of adding energy to the system by doing work. Because we have said we can increase internal energy by heating or by mechanical means through work, or we can decrease internal energy by leaving the system to lose heat to the surrounding, or by leaving the system to do work to the surrounding. So in both cases, the change in internal energy depends on the heat either supplied or lost by the system, and the work done on the system or the work done by the system. Therefore, the increase in internal energy is equal to the energy supplied by heating plus the energy supplied by doing work on the system. This is what we call, or this statement is what we call the statement of the first law of thermodynamics. The increase, I'm saying increase because this law has sign conventions. The increase in internal energy is equal to the energy supplied by heating plus the energy supplied by doing work on the system. If I maintain this statement the way it is, then the sign convention would look like this. Delta U is positive, Q is positive, W is positive, which means increase in internal energy is equal to the heat supplied by heating plus the work done on the system. That is called the first law of thermodynamics. Remember from ideal gases, I think we mentioned that the work done by an expanding gas, for example, or the work done on a compressed gas is given by the pressure times change in volume, where P is pressure and delta V is the change in volume. So we now know the first law of thermodynamics as being equal to Q plus W as the first law of thermodynamics. In an exam, you can state the first law of thermodynamics as delta U equals to Q plus W, and then you define these letters. For example, delta U is increase in internal energy, Q is heat supplied to the system, or heat supplied by heating the system, and plus W, which is the work done on the system, or the work done to the system. So let's try to understand this even in more details. Let's try to understand the first law in more details by taking notes. Number one, in thermodynamics, it is necessary to define the system under consideration. The system could be an ideal gas, the system could be water being heated in an electric kettle. We have to define the system we are considering. So for example, the system may be an ideal gas, so you must be very careful to define the system, because if it is an ideal gas, we know that the potential energy component is zero, it doesn't contribute to the internal energy. It could be an ideal gas in a cylinder fitted with a piston, or an electric heating coil in a container of a liquid. So defining the system being considered here is very important for us to know how the internal energy changes. Also, I want you to recall what we have just mentioned earlier on, that work is done when energy is transferred by mechanical means. You are compressing the system, that is a mechanical mean, or the system is expanding, that is a mechanical mean. Movement is involved in that case, because work is force times distance in the direction of the force. So we have just seen that heating is a transfer of energy due to a difference in temperature, and we shall see this in more details under the next part, which is going to be called temperature. So heat flows from a region of high temperature to a region of low temperature naturally. And yet, for work, energy is transferred to the system mechanically. And we have also mentioned that internal energy is the sum of the kinetic and the potential energies of the various particles which make up the system. Do not forget what I mentioned earlier on, that for a system consisting of an ideal gas, which we shall always consider many times, the internal energy is simply the sum of the random distribution of the kinetic energy of all the molecules or the atoms which make up the gas. Because I mentioned that there is no potential energy since the intermolecular forces between the molecules are negligible. So before you use the first law of thermodynamics, you should have these concepts on your fingertips. If you are dealing with an ideal gas, which is the system that you have defined, just recall or remember that the internal energy of an ideal gas only depends on the kinetic energy of all the molecules which make up the system. In summary, so by heating or doing work, we are adding energy to the system. And by conservation of energy, this energy cannot just disappear, it must be transformed to another form of energy. That's how we ended up with the internal energy. So it either appears an increase in internal energy of the gas, that is, the total kinetic energy of the molecules is going to be increased if the gas is ideal. Because if we add heat by doing work, if we add heat to the system, or if we do work onto the system, the energy or the energy we are adding to the system will not just disappear, but this energy must be transformed to other things or to something else. And that's why we said if these two are done, work and heating, there could be an increase in internal energy. And the increase in internal energy for an ideal gas will be the total increase in total kinetic energy of the molecules that make up the ideal gas. But if the total kinetic energy of the molecules is increased, what happens to the average kinetic energy of the molecules? Of course, the average is also increased. If you recall from ideal gases, we saw that the average kinetic energy of the molecules, which make up a gas, is given by 3 over 2 times kT. So it means if the average kinetic energy of the molecules increases, it means the temperature of the temperature also increases. So this means if the average kinetic energy of the molecules increases, then it means the temperature increases, because the average kinetic energy of the molecules is a measure of temperature. Of course, if I want the average kinetic energy of all molecules, I would multiply this by the number of molecules. So the average kinetic energy of the molecules is a measure of temperature. The addition of energy to the ideal gas shows up as an increase in its temperature. So we have added heat, or we have done work onto the gas to increase the internal energy, which means we have increased the total kinetic energy of the molecules if the gas is ideal. And if the total kinetic energy of the molecules increases, it means the average kinetic energy of the molecules has increased. If the average kinetic energy of the molecules has increased, it means the temperature has increased, because temperature is the average kinetic energy of the molecules. Hence, increase in internal energy of a system is equal to the sum of the thermal energy added to the system and the work done on the system. And this is the first law of thermodynamics. Of course, there are other laws. There is the second law of thermodynamics, which you may see in chemistry if you are doing chemistry, or if you are in another curriculum, you may see all the other laws. But for us, we shall only concentrate on the first law of thermodynamics. Now, this law comes with the sign conventions that we are here to discuss. What are these sign conventions that we shall consider while dealing with this law? Remember, the increase in internal energy is equal to Q plus W, where Q is heat supplied to the system or heat lost by the system, and W is going to be the work done. Now, what sign conventions come with this law? If Q is positive, a positive value of Q means that thermal energy is added to the system. So if we take Q as positive, it means heat is added to the system. Heat is supplied to the system. If we take W as positive, it means work is done on the system. Work is done on the system. For example, a gas is being compressed. If a gas is being compressed, work is done on the gas. So the work done is positive. If we get a positive value of delta U, that is an increase in internal energy. So delta U means the direction of the internal energy is an increase. Many times the examiner will ask you to state the direction of the internal energy. It is an increase if it is a positive value. And a negative value of delta U would mean the internal energy is decreasing, or it is a decrease in internal energy. If we have an heat released or given out by the system, the sign convention will be a negative value, negative Q. So negative Q means heat leaves the system. And lastly, negative W would mean work is done by the system. For example, when a gas expands, it is doing work to the surrounding, and the work done by the gas to the surrounding is considered to be negative. So this sign convention is going to be very, very important in calculations. Before we use the sign convention, let's briefly talk about the application of the first law of thermodynamics in everyday experiences. Number one, we can talk about an adiabatic process. We don't need really to know much about the adiabatic process, but what is an adiabatic process? An adiabatic process is one which occurs with no thermal energy entering or leaving the system. So if a system occurs where no thermal energy enters or leaves the system is called, the process is called an adiabatic process. And if that is true, no heat enters or leaves the system, that means Q, the Q part of the first law of thermodynamics will be zero. So if no heat enters or leaves the system, Q is going to be zero. And if we talk about the first law of thermodynamics, delta U is equal to Q plus W. So Q will be zero. That means delta U is going to be equal to positive W. Now, the internal energy will either be an increase or a decrease depending on the value of W. And if work is done onto the system, W is positive, so the internal energy will be positive. That will be an increase. If the system expands, work is done by the system, W will be negative, so the internal energy will also be negative, which will be a decrease. But for this particular case, the internal energy increases because the total kinetic energy of the molecules increases. Thus, the average kinetic energy of the molecules increases, and hence the temperature increases. So, if the gas is ideal, we can easily and simply obtain the internal energy of the gas by considering the total kinetic energy of the molecules, Ek times n, where n is the number of molecules, and this is equal to 3 over 2 kT times the number of molecules. This would give us the total kinetic energy of all the molecules which make up the gas, which is going to be equal to the internal energy of the gas, if the gas is ideal. Because if the internal energy increases, the total kinetic energy increases, which means the average kinetic energy increases, and hence the temperature of the gas increases, because temperature is the average kinetic energy of all the molecules which make up the gas. So an adiabatic process or adiabatic change can also be achieved by moving a piston. Sorry about this, my pen has stopped responding, so I have to find the way out. So I was saying an adiabatic change can also be achieved by moving the piston rapidly. For example, if a gas is dropped into a container, into a frictionless, into a cylinder like this one, where it is trapped by a piston, we can achieve an adiabatic process. If here there is a gas, we can achieve an adiabatic process or an adiabatic change by moving the piston in and out rapidly. For example, it could be pumping air into a bicycle tube, and you are doing it very rapidly. That means you are not allowing time for the molecules to lose the kinetic energy they have acquired, and therefore there is no heat. There is no heat. There is no heat leaving or joining the system. That is an adiabatic process. But we are not so much interested in knowing about an adiabatic process at this level because it's not part of the curriculum. Another application you can also think about, also think of an electric kettle containing water. Here the element provides thermal energy to the system, that is the heating element, and the quantity Q in the first law is positive because heat is added to the system by the heating element. And by sign convention, Q will be positive. And if we say that there is no mechanical work being done by the water, because the volume of the kettle does not actually change, so it means the work done in that case when heating water is going to be zero. And therefore Q will be the only quantity which will be determining the change in internal energy. So from delta U equals to Q, then if Q has been added to the system by the heating element, so it means Q is positive, which will also make delta U to be positive. Therefore, you would say that the internal energy is actually an increase. So the internal energy increases, which also means the temperature of the system increases. Note: when a substance changes from solid to liquid, that is, there is a change of state, the intermolecular bonds are broken and thus increasing the potential component, the potential energy component of the internal energy. So the internal energy increases. However, um, during the melting process, the temperature does not change. Therefore, the kinetic energy of the molecules does not change because the kinetic energy of the molecules is what determines the temperature, or the temperature determines the kinetic energy of the molecules and vice versa. So if the temperature is not changing, it means the kinetic energy of the molecules has not changed. If the kinetic energy of the molecules does not change, it means the temperature has not changed. But heat is being supplied. Where is the heat ending up? The heat is going into breaking the intermolecular bonds between the molecules. So the heat is the energy supplied is breaking the intermolecular bonds, increasing the potential energy component. So the internal energy still increases in that case. So whenever there's a change of state, internal energy also increases, but this time it's not due to the kinetic energy of the molecules because the temperature does not change. It is because the energy supplied goes into breaking the bonds, increasing the potential energy between the molecules. And by the way, most substances expand on melting, and thus it means the external work is done. And of course, the external work done is negative, which would cause a decrease in internal energy. And by the first law of thermodynamics, thermal energy must be supplied to the system, and this thermal energy which is supplied is what we call latent heat. The word latent means hidden, or it is concealed. Concealed or hidden. We don't physically see the effect of the heat being supplied because we don't see any change in temperature, but the heat being supplied is actually going into breaking the bonds. It is going into breaking the bonds, thereby increasing the potential energy as the bonds are being broken. So, I want you to note that because most substances expand when they are melting, that means there is a change in volume. So volume changes associated with evaporation are much greater than those associated with melting. Because for melting, the molecules slightly are still close to each other because they are changing from solid to liquid. But yet for vaporization, the molecules have to escape to the vapor phase to move farther away from each other. That means the volume changes associated with melting are smaller than the volume changes associated with evaporation or vaporization. That's why it means the external work done is much greater during vaporization, and thus the latent heat of vaporization is going to be much greater than the latent heat of fusion. We shall talk about latent heat of vaporization and latent heat of fusion later on in the next chapter, which is temperature, and that's where we shall discuss real thermal properties in more details. So many substances many substances expand on melting, which means there's an increase in volume. That means there's an external work done to the surrounding. And the volume changes associated with melting are much smaller than the volume changes associated with evaporation or vaporization. Because during vaporization, the molecules must move farther apart, farther away from each other. Yet, during melting, the molecules just slightly move far from each other. They are still closer, but they have just moved slightly far from each other, so the volume slightly increases. Yet, if the molecules are to escape into the vapor phase, they must move farther apart. They must move farther apart, thereby causing a greater increase in volume. So that means the heat required to just move the molecules slightly far from each other is much less than the heat required to make the molecules move farther apart, farther away from each other. That's why we say um, the latent heat of vaporization is much greater than the latent heat of fusion, because latent heat of fusion is concerned with melting, and the latent heat of vaporization is concerned with vaporization that is from liquid to gas. I'll talk about this in more details in the next chapter. But the examiner may ask you, why is the latent heat of vaporization greater than the latent heat of fusion? And I've already talked about this. When evaporating, greater change in separation of atoms or molecules, that is a greater change in volume, occurs, giving an increase in potential energy and thus increased internal energy. Greater change in volume occurs as the gas molecules push back the atmosphere, thus the external work done is much greater. Because the gas molecules must push against the atmosphere for them to be able to escape further away from each other, then they would cause a greater change in volume, and therefore the greater external work is done. So it means it would require much more energy to be supplied. That's why we say the latent heat of vaporization is greater than the latent heat of fusion. Of course, latent heat is the amount of heat required to change a substance from one state to another without any change in temperature, as we shall see in more details in the next chapter. Okay, I have said a lot of things, and finally, I just want to give a few examples. So these examples are basically going to use the first law of thermodynamics and the sign conventions, and that will be something which is very easy. 200 joules of thermal energy is added to the system. So because it is added to the system, this is going to be positive, which does 150 joules of work. That means the system does work. Because the system does work, the work done by the system is negative by the sign convention. Find the change in internal energy of the system. So by the first law of thermodynamics, the change in internal energy is equal to Q plus W. So the change in internal energy is going to be Q, which is positive 200 plus W, which is negative 150. So that means the change in internal energy is going to be positive 50 joules. Of course, the direction of this change in internal energy is an increase. It is an increase because it is positive. Okay. Number two, an isothermal change is one which takes place at a constant temperature. Remember, if there is no change in temperature, it means there is no change in internal energy. If the change in temperature is zero, it means there is no change in internal energy. But they are saying an isothermal change is the one which takes place at a constant temperature. Explaining why in any isothermal change, the change in internal energy is zero. In such a change, 200 joules of thermal energy is added to a system. How much work is done on or by the system? So for an isothermal change, explain why in an isothermal change, the change in internal energy is zero. So we know that the change in internal energy is equal to because this is, if we assume that this is the system is an ideal gas, for example, for an isothermal change, the change in internal energy is equal to zero because the change in the temperature is equal to zero. We know that change in internal energy depends on the change in temperature. For an isothermal change where the change in temperature is zero, it means the change in the kinetic energy of the molecules is going to be equal to zero. Because internal energy is the sum of the random distribution of the kinetic energy of the molecules, because the change in temperature is zero, it means the change in kinetic energy is zero, which means the change in internal energy is going to be zero. That is as simple as that. In such a change, 200 joules of thermal energy is added to the system. So this is going to be positive. How much work is done on or by the system? So we are not sure whether it is done on or it is done by the system. So using the first law of thermodynamics, change in internal energy is equal to Q plus W. Because it's an isothermal change, the change in internal energy is zero, so we shall say zero equals to Q. They say the Q is positive, which is positive 200 joules, plus W, which we don't know, let it be W. So when I take W on one side, so W is going to be equal to negative 200 joules. So this work is done, 200 joules is done by the system. So 200 joules of work is done by the system. The reason as to why it is done by the system is because the work done is negative. Okay, the negative here is showing that the work is done by the system. The first law of thermodynamics may be expressed in the form delta U equals to Q plus W. Explain the symbols in this expression. So this one plus delta U means an increase in internal energy, plus Q means a decrease in internal energy. Sorry, I don't know what I'm thinking. Plus delta U means heat supplied to the system, heat added to the system, or heating of the system. Heat supplied to the system, heat added to the system, heating to the system. Plus W means work done on the system. It is on the system. Minus W means the decrease in internal energy. Minus Q means a heat released by the system, or heat lost by the system. Then minus W means work done by the system. Work done by the system. Okay, so that is the sign convention. You'll find such a question many times in the exams. A gas is heated by supplying it with 250 kilojoules of energy. At the same time, it is compressed so that 500 kilojoules of work is done on the gas. So because this is work done on the gas by conversion, that is positive. and a gas is heated by supplying it with. This is added to the system, so that is positive. Calculate the change in internal energy. So the change in internal energy is equal to Q plus W according to the first law of thermodynamics. And this is going to be Q is positive, so that is 250 positive. W is positive because the gas is compressed, so this is going to be plus 500, which gives us 750 kilojoules. So that is an increase in internal energy. This is an increase in internal energy. It is an increase because delta U is positive, or the result we have obtained is positive, so it is an increase according to the sign convention. Okay, that is part A. Part B, some gas is heated as before with 250 kilojoules of energy. So that means still this is positive. This time the gas is allowed to expand so that it does 200 joules of work. Because the gas expands, this heat is negative according to the sign convention. This work done is negative. Calculate the change in internal energy. So change in internal energy is going to be equal to positive, or it is Q plus W, which is going to be 250 plus negative 200, which still gives us, I think this gives us 50 kilojoules. Now, even though the change in internal energy is lower than before, it is still an increase in internal energy. However small, it is still an increase because it is positive. Okay. When the gas is kept from when the gas is taken from state P to R, that is following this side P to R by stages PQ and QR, 8 joules of heat are absorbed by it. So this is absorbed by the gas, so this is positive, it goes into the gas. 3 joules of work are done by the gas. This is going to be negative because it is the gas which is doing work. For stages PS and SR, that is if the gas is taken through the stages this side, 1 joule of work is done by the gas. Because it is the gas doing work, the 1 joule is going to be negative. Determine if heat is released or absorbed and the amount. Okay, so I want first of all for us to notice what is happening here. P to S, the volume increases. The volume increases, the gas system does work. So here the work done is going to be negative, P to S. And S to R, there is no work done because the volume is constant. P to Q, there is no work done because the volume is constant. Q to R, there is work done by the gas because the volume increases, and that work done is negative. So let's first start with the stages P, PQ, and QR. Using the first law of thermodynamics, delta U is equal to Q plus W. We have that the change in internal energy, which is delta U, is going to be equal to Q, which is positive 8 joules, plus W, which is negative 3. The change in internal energy is going to be 5 joules. Because whether you move from P to Q to R, the temperature at R is the same whether you move from PQ, QR, or PSSR. So it means the change in internal energy is going to be the same because we all started from P and we're ending at R. So the change in the temperature from P to R is the same for whatever direction you take. So it means even if I follow PSSR, the change in internal energy is going to be the same. So let's now follow PS and SR. Using the same equation, change in internal energy is equal to Q plus W. The change in internal energy is going to be 5 joules equals to Q. So we want to find Q, so I'll leave Q here plus W, which we said because For stage PS and SR, minus 1 joule of work is done because it is done by the gas. So this is going to be plus negative 1. So this makes Q to be equal to positive 6 joules. Because Q is a positive value, determine if heat is released or absorbed. So heat is absorbed. Because positive means heat is added to the system, so heat is absorbed. So the heat is absorbed by the system, as simple as that. And that is the heat amount absorbed is 6 joules. A fixed mass of an ideal gas undergoes a cycle PQRP of changes as shown below. So this is the cycle. State the change in internal energy of the gas during one complete cycle. So if we start from P at a temperature say T1, we move to R, we come back to Q, and we come back to P where the temperature is T1, it means the change in temperature equals to 0. The initial and the final temperature are the same. And since the initial and final temperature are the same, then it means the change in internal energy is going to be 0 because for an ideal gas, the change in internal energy depends on the kinetic of the molecules, and the average kinetic of the molecules is the temperature. So if the initial and final temperature are the same, then the change in internal energy is going to be 0. So I would simply say for the first part, the change in internal energy equals to 0, reason being the initial and final temperature are the same. Or you could say the gas goes back to its initial temperature. Or gas goes back to its initial temperature. Then calculate the work done on the gas during the change from P to Q. So P to Q, you see that the volume is decreasing. So a decrease in volume means the gas is being compressed. We can predict that that work done is going to be even positive. So the work done is equal to pressure times change in volume. The pressure is 4 times 10 to the power of 5 pascals. The volume changes from 8 times 10 to the power of minus 4 to 2 times 10 to the power of minus 4. So I'll just press my calculator. So this work done is going to be 240 joules, and this is positive. So the work from P to Q is 240 joules. Some energy changes during the cycle P, Q, R, P are shown. Complete the table. So I'll just sketch here the graph was like this, somehow like this, where this was P, Q, R, and it was in that direction. So we have seen that P to Q, the work done is positive 240 plus 240 joules. We can find the increase in internal energy here. The increase in internal energy is equal to Q plus W, which is equal to 240 plus negative 600, which gives us here the work done is going to be minus 360. So here we have minus 360. I don't want to write this in the table because it is not professional. So that is minus 350. I just used the change in internal energy is equal to Q plus W, which is equal to 240 or negative 600 plus, sorry, negative 600 plus positive 240, which gave us that. Then the second one, we use again the same formula. The change in internal energy is going to be 0 plus 720, which gives us positive 720. But remember, the total change in internal energy is equal to 0, total. So that means when I sum up all these, I will call this one x. So it means x plus 720 plus negative 360 should give us 0, which means x is going to be equal to negative 360. So here we have 360 joules, positive. Then we now move backwards using the change in internal energy equals to Q plus W. So the change in internal energy is 360 positive. Sorry, it is negative, not positive. This is negative. Negative 360, that is negative 360, equals to Q, which is positive 480, plus W, which we don't know. So W is going to be equal to negative 360 minus 480, which gives us negative 840. So the answer here is negative 840. I think I quoted this from past papers. And I think this should be the last question in this thermodynamics. This is the end of thermodynamics as a lesson. Do not forget to watch the solved past paper questions.